Hello everyone. Now we have to discuss the problems on three-phase circuits. So problem 1 is using Thevenin's equivalent circuit, determine the RMS value of the voltage across this 100 ohm resistor after the switch is closed in the three-phase circuit shown in figure. So here we have star connected supply, star connected load, but he wants the Thevenin equivalent circuit between this R and this neutral, right? So we have phase impedance of 300 ohms, 300 ohms, 300 ohms, but we have between R and N we have 100 ohms of resistance, and he provided that the line to line voltage is what, 400 volts, that is the phase voltage is what, 400 by root 3, right? Now we have to get, we all know that to get the Thevenin's equivalent circuit, first we have to get Thevenin's equivalent voltage and Thevenin's impedance. Later we have to write the equivalent circuit of Thevenin equivalent circuit. We have to draw that circuit. Okay, first we have to, VTH is what he provided, which is equals to V phase, right? That is 400 by root 3, which is equals to what, 231 volts of Thevenin's voltage, that is phase voltage, right? Why it is called as Thevenin's voltage? So between these two we have VTH. See, between this two we have to calculate VOC, right? When we open this load resistor, obviously we have to calculate the voltage of this phase, which is equals to V phase only. Therefore VOC is equals to V phase. That's why VTH, which is equals to V phase, that is 231 volts, right? Now to find ZTH, replacing all other independent voltage sources by short circuit, right? We all know that to calculate equivalent resistance we have to replace all other independent sources by their internal resistances. Here we have voltage sources, therefore we have to replace them by short circuit, right? Therefore this point and this point are interconnected. Then the circuit becomes, let us say we have load, right? Therefore this point, that's it. This is given as 300, right? Then ZTH is what, between these two we have to calculate ZTH, that's it, right? Therefore what is the value of ZTH? See, by looking between these two terminals, these three branches are connected in parallel, right? Or if you have any confusion, just allow some current to these branches, then you have clear idea. Then you can say that ZTH, which is equals to 300, which is parallel with 300, which is parallel with 300. Finally we got 300 by 3, that is ZTH as 100 ohms. That's it. Next we have to get Thevenin's equivalent circuit, that is Thevenin's voltage is connected in series with what, Thevenin's impedance In addition with that, we have to reconnect the removed load branch. What is that? That is RL, right, which is equals to what? 100 ohms. This is ZTH. This is VTH. This is ZTH, right? That's it. Finally, we have a current. But he wants the voltage across this resistor. Okay. Therefore, voltage across 100 ohm resistor is V100 ohm, which is equals to, we have to apply voltage division principle. VTH is what? 231, right? 231 into current branch resistance, that is 100 by RL plus ZTH, that's it, right? Which is equals to 231 100 by, what is the value of RL? 100 plus ZTH is what? 100. So we got 115.5. The answer is what? 115.5 volts. This is voltage across 100. What is the value of current? Simple, VTH by ZTH plus RL, right? Like that, current is equals to VTH by ZTH plus RL. That's it. 231 by 200. That is nothing but what? 1.31, right? The answer is 1.31 amps. This is about first problem. Next, a set of 3 equal resistors, each of value Rx, connected in star, right, of given figure, consumes the same power as the unbalanced delta connector load shown below. Then the value of Rx is what? Means what? We have a connection of star in this branch, right? Let us say okay, Y to Y, B to B and R to R. We are having what? Equal value of resistance. Let us say Rx, Rx, Rx. That's it. We have to calculate the value of Rx. That's it, right? So by looking at the load, we have to conclude that the load is unbalanced load, right? We have 100 ohms, we have J50, we have capacitive impedance. The load is not equal, right? Therefore, we conclude that load is unbalanced, right? We have to calculate the value of resistor Rx. That's it. That is only resistor consumes real power, right? But not capacitor inductor. That's it. Only resistor consumes real power. Therefore, power consumed in unbalanced, therefore power consumed in unbalanced delta connector load, which is equals to what? We know that V phase square by R, because in case of delta, V phase which is equals to V line, since V phase which is equals to V line. That's it, right? Therefore, power in delta connection, power in delta connection is what? VL square by R, right? Which is equals to 400 whole square by R, which is equals to, R is given as what? 100. See, it is 100. Only resistor consumes real power. Therefore, across we have to calculate that power. Okay, it is given as 100. This is 100. Therefore, we got 1600 watts. The power in delta connection is what? 1600 watts. We know that power in delta connection should be equals to what? 3 times of power in star, right? Therefore this is what? Power in delta, which is 3 times of power in star, which is equals to 1600, which is equals to 3 into P in star is nothing but what? We have P phase square by R, right? Therefore we can write R, which is nothing but Rx in star connection, right? So Rx, which is equals to 3 into V phase square by 1600. Therefore Rx can be write root 3 V phase by 40 whole square. Obviously we can write, we all know that Rx, which is equals to root 3 V phase is what? That is nothing but VL by 40 whole square, since VL is equal to root 3 V phase in star connection, right? That's why we have that value. Rx, which is equals to VL is what? Given that 400 by 40 by whole square. Therefore Rx is what? We got 100 ohms. So the value of resistance in star connected supply system is what? 100 ohms. That's it. Next problem is, two resistors of equal value are connected in series across the lines B and C of a symmetrical 3-phase 400 volt system. What is the magnitude of the voltage between the line and the junction of the resistors? Means, that is, the circuit is what? Let us say this is A, okay? This is B phase, this is C phase, this is B, this is C, right? Means he provided two resistors of equal value are connected in series across the lines B and C. Let us say this is like this, right? So this is the point, that is neutral point. That's it. Okay, across the lines B and C of a symmetrical 3-phase 400 volt system, what is the magnitude of the voltage between the line A and the junction of the resistors? This is the junction, right? Let us say this is N, okay? This is, he provided that this is what? Given that 400 line to line voltage. Then what about this voltage? Let us draw in a fish pale, okay? Before that we have to write, given V line to line is what? 400 volts. That is, the connection is one phase, another phase. Let us say this is A phase, B phase, C phase. In between B and C we have the equal value of resistors which are connected in series, and the junction point of those two series connector resistors is nothing but, let us say, N, right? He given that the line to line voltage is nothing but 400 volts line to line. That's it. Then he wants what? What is the magnitude of the voltage between the line A and the junction point of that? So he wants the voltage between what? VAN. He wants VN is what? That is the question, right? This is given as, let us say, R, okay? Between this, given that 400. Between two lines, we have 400. Therefore, we have to get VAN, right? VAN is nothing but what? Summation of VAB and VBN, right? Vector addition. Vector addition only. That is, let us say VAB at an angle 0, vector addition. Okay. This is what? VBN at an angle, let us say, minus 120. So from this is what? 400, right? plus 200 at an angle minus 120. We can say which is equals to 300 minus j 100 root 3. That's it. So from this we have what? VAN, which is equals to 200 root 3. Forget about the phase angle. He asked for what? Magnitude only. So this is the magnitude of VAN. That's it, right? Next, fourth one. A three-phase, three-way supply feeds a star-connected load consisting of three equal resistors. If one of the resistors is to be removed, then what is the reduction in power as compared to the original power? He given that what? Star only. In addition with that, here I am providing star and delta. Okay, star and delta means star and delta connected load consisting of three equal resistors. If one of the resistors is removed, then what is the total reduction in power? We have to calculate. Right? This is ESE 2007 problem. First, we have to calculate when all the resistors are present. When all the resistances are present, what is the power? P is equals to what? 3 P phase square by R, right? Which is equals to 3 into V phase is nothing but what? In case of star connection, VL by root 3 whole square by R, right? Which is equals to what? VL square by R. That's it. In case of star connection. Okay, in case of star connection, that's it. When one of the phase resistance is removed, so when all are present, this is the power. When one of the phase resistance is removed, then the power is what? P is equals to, only we have a 2VL by 2 whole square into 1 by R, that is VL square by 2R. Sir, what is this, sir? Since we can write the reason. Since when one phase resistance is removed, voltage across resistances is VL by 2, that is okay. How we can get VL by 2? Let us see. For example, right, this is one phase, this is another phase, this is open circuited phase, right? That's it. So one of the phases is open circuited, another circuit open, that is removed, that is R. So between these two is nothing but what? VL, right? That VL is nothing but what? VL by 2. This is the circuit diagram for this. Okay. Therefore, reduction in because why it is VL by 2? See, those two are connected in series. Just we have VL by applying voltage division principle. What is the voltage? VL by 2. That's it. Across phase, this is VL by 2. This is VL by 2. Let's write that point. VL by 2. This is VL by 2. Clear? Total voltage is nothing but what? VL. That's it. Now it's clear, right? That's it. Therefore reduction in power, which is equals to VL square by R minus VL square by 2R, right? What is the power? VL square by 2R from 1 and 2 by VL square by, so total power minus by reduction power by total power into 100, which is equals to what? Reduction in power, which is equals to 50%. That is in star connection, that is in star connection the power reduced is 50%. Like that, in case of delta connection, in delta connection, power reduction, which is equals to, we know that 3VL square by R minus 2VL square by R, right? Which is equals to what? VL square by R. Only that is how much? 33.33% is reduced. Is but in case of star 50% is reduced. In case of delta only 33.33% is reduced, right? That is by 3VL square by R. You can write that by R. You can write by which is equals to what? 1 by 3, right? That's it. That is 33.33% is reduced in delta connection. That's it. Next problem is a RMS voltage in a three-phase star circuit is given by 231 volts phase to neutral, that is phase voltage. Write the instantaneous voltage expression, that is Vm sin omega t form, right? If the current in each phase lags the corresponding phase voltage by 30 degrees, what are the expressions of instantaneous currents? Okay, that is solution. Given that star connection, in star circuit line to line, which is equals to root 3 V phase to neutral, right? Which is equals to root 3 into, given that this is 231, which is equals to what? 400 volts. That's it, right? Therefore the line voltage in case of, that is, this is what? RMS, right? Therefore in order to get maximum value, so root 2 VRMS, right? Vm by root is nothing but VRMS. This is RMS, right? This is RMS. To get R value, that is line to line, in case of star, let us say we all know that VRY, which is equals to root 2 into 400 into sine omega t. It is why it is omega t reference, right? Like that, p by b, which is equal to same root 2 into 400 sine omega t. What is the problem? Yeah, now it's okay. Here v of b is what? Root 2 sine omega t minus 120, right? Minus 120, like that. VBR, which is equals to what? Root 2 400 sine omega t minus 240. We all know that, right? These are the instantaneous values. That is, we can write VRY simply, which is nothing but root 2 into 400 at an angle 0. P by B, which is equals to what? Root 2 into 400 at an angle minus 120. PBR is nothing but what? Root 2 into 400 at an angle minus 240. That's it. Now, phase currents. We all know that in case of star connection, phase current would lags phase voltage by 30 degrees, because he provided that what? If the current in each phase lags, see, if the current in each phase lags the corresponding phase voltage by 30 degrees, that's why the power factor is what? Lagging. As the phase currents would lag phase voltage by 30 degrees, therefore phase current, which is equals to what? Let us say IR, right? Which is equals to, this is 231 by Z is what? Assume, because V by Z into root 2 into sine omega t, now minus 30, because why minus 30? Current lags phase voltage by 30 degrees. Why it is root 2? 231 is nothing but RMS. Root 2 RMS is nothing but maximum value. Vm sine omega t is nothing but representation, right? Assume Z is equals to 1 ohm. Okay. Therefore, IY is nothing but what? 231 into root 2 sine omega t minus 120. IB is what? 231 into root 2 sine omega t minus 240. That's it. Sorry, minus 120 minus 30. We have to add 30, right? This is what? 120. This is what? The phase current would lags phase voltage by 30 degrees. Here we are providing what? Line. So in star connection, line voltage leads phase voltage by 30 degrees, right? Here line voltage is 30 degrees, 0, minus 120, like that, minus 240. What about phase voltages? Yeah, we have VR at an angle minus 30. This is minus 90. Okay, I have mistaken. See, here we have what? This is nothing but line voltage. We know that VL leads V phase by 30 degrees in case of star connection. Therefore, to get phase voltages, obviously root to 400 sin omega t minus 30. To get phase voltage of B, root to 400 sin omega t minus 120 minus 30 minus 150, right? That's it. We can get, therefore, phase voltages VR, which is equals to what? Root 2 into 400 sin omega t is nothing but reference, right? Now it is, which is lags line voltage by 30 degrees. That's why minus 30. Vy is what? Root 2 400 sin omega t minus 120 there, minus 120 minus 30, which is equals to what? Root 2 400 sin omega t minus 150. Vb is what? Root 2 400 sin there omega t minus 240 minus 30, that is minus 270. This is phase voltage representation in instantaneous forms. Now we have to get the phase currents. We all know that in case of star connections, phase current should be equal to line current. Now it's clear. Phase current, right? Given that phase current lags phase voltage by 30 degrees, right? Therefore, phase current IR should be equals to what? Root 2 times of I phase. Before that, I have to write one point. I phase is what? P phase by Z, right? Assume Z is equals to 1 ohm, or that's it. Now we have to write the phase currents. IR, which is equals to what? This 231 is nothing but RMS. But what is the representation? Vm sin omega t, that is root 2 into 231 sin. Now we have our omega t minus, which lags phase voltage by 30 degrees. What is the phase voltage? Omega t minus 30. Now we have what? Omega t minus 60. That's it. Okay. Next, Iy, which is equals to what? Root 2 231 sin omega t. We have what? Minus 150 minus 180. Ib is what? Root 2 into 231 sin omega t minus 300. That's it. So we have represented all voltages, phase voltages, line voltages, and phase currents, line currents in instantaneous voltages, instantaneous forms, right? This is about the problem. Okay. Next, a balanced 3-phase load draws 8 kilowatts at lagging power factor of 0.8, right? If the line voltage applied is 440 volts, find the complex power and the line current. We all know that complex power, which is equals to what? 3 phase. This is equals to what? Root 3 VLIL volt amperes, right? So given that VL is what? 440 volts. S is equals to P plus JQ, right? That is, S is equals to what? Mod S cos phi plus mod S sin phi, which is nothing but S, right? and the power factor is given by what? 0.8 lagging, and given power factor is what? 0.8 lagging. Therefore phi is equals to cos inverse 0.8 is nothing but 36.8 degrees. The phi is what? 36.8. Now we have to get P is what? S cos phi. P is what? S is what? P by cos phi. Given that, yeah, a balanced 3-phase load draws 8 kilowatts at a lagging power factor of 0.8. So given that what? 8 kilowatts is nothing but active power, right? Okay. So this is 8. From this, S cos phi is what? 0.8. Therefore S is what? 10 at an angle 36.8. We have 10 at an angle 36 kilowatt amperes. That's it. And IL is what? Mod S root 3 440 from this, right? From this, which is equals to 10 at an angle 36.8 by root 3 440. From this IL, which is equals to 13.12 amperes. That's it. This is about the complex power and the line current. That's it. We have the relation. From this relation we are going to get the value of S, and we have the power factor, we have the line to line voltage. That's it. Next, the power readings of 2 wattmeters are plus 15 kilowatts and minus 4 kilowatts for a 3-phase load. If the supply voltage is balanced 440 volts, find the true power drawn by the load and the power factor and the line current. So we have to calculate the real power P, power factor and line current. Okay. So from this we have to write this is very important problem, because we have the negative power of 1 wattmeter reading, that is minus 4 kilowatts, right? We have positive power, we have negative power. We all know the first we have to calculate the true power, that is we all know that the formula for true power is what? W1 plus W2. True power, which is equals to what? P, which is equals to W1 plus W2, which is equals to what? 11 minus 4. Therefore P is equal, 15 minus 4. This is what? 15, right? 15 minus 4 is 11 kilowatts of true power. That's it. We have completed true power. Next, we have to calculate the power factor. To calculate the power factor, first we need to calculate the phase angle, right? That is phi is equals to what? Tan inverse root 3 W2 minus W1 by W1 plus W2 or W2 plus W1. That's it. So from this, phi is equals to tan inverse root 3 W2 15 plus 4, right, by 11. That's it. 15 into root 3 into 15 plus 4 by 11. We have what? Tan inverse root 3 19 by 11, right? That is phi is equals to tan inverse 2.99. Okay. Therefore phi is equals to what? 71.52 degrees. Phi is equals to 71.52. Therefore what is the power factor? Cos phi is what? Cos of 71.52, which is equals to 0.317 lagging, right? That's it. Next we have to get line current. Line current is what? S is equals to what? Root 3, sorry, P. We have real power, right? P is equals to root 3 VL IL cos phi. From this to get IL, P by root 3 VL cos phi. That's it. So IL is what? P is what? 11 kilowatt, right? Into 10 cube by root 3. VL is what? Given that 440 volts into cos phi is what? 0.317, which is equals to IL is what? 45.53 amperes. So IL is what? 45.53. So finally what we have? True power is what? 11 kilowatt. Power factor is equals to what? 0.317 lag, and line current, which is equals to what? 45.53 amperes. That's it. Before that, it may be noted here, one of the wattmeter reading is positive, another one is negative, right? If for example this wattmeter reading has been taken reverse by reversing the pressure coil, right? That is, if W1 is negative, directly the tan phi is what? W2 plus W1 by W2 minus W1, which is equals to root 3, which is nothing but 19 by 11. That is W2 plus W1 by W2 minus W1 into root 3. At that case also we are going to get 2.99. Okay. See here, one of the wattmeter reading is negative. Therefore, we have to reverse the terminals of potential coil. That's it. Okay. That's why we have the value of phase angle 2.99. This is about true power, power factor and line current. Next problem is, if a balanced 50 volts 50 Hz 3-phase voltage is applied across 2-phase load as shown in figure, find the power reading in wattmeter. That's it. So here the wattmeter is connected between what? A and B. Now we have to calculate the phase line voltage VAB and the IA dash. Means to calculate the wattmeter reading, we have to get the line voltage between A and B and the series current, that is VAB into IAA dash. That's it. Okay. Given between VAB is what? 50 at an angle 0, right? And VBC 50 at an angle minus 120. VCA is nothing but 50 at an angle 120 degrees. Clear. Given that between A dash and B dash 5 plus J4, like that between A dash and C dash 5, load is unbalanced, right? Then we have to calculate the required data. That's it. Given VAB is nothing but what? 50 at an angle 0, VBC which is equals to 50 at an angle minus 120 volts, VCA which is what? 50 at an angle plus 120 or minus 240, right? This is completed. Therefore, next, what about the impedances? Given that ZA dash B dash which is equals to 5 plus J4 which is equals to 4.64 38.7 ohms, like that Z A dash C dash which is given as pure resistive load, that is 5 ohms only, right? Next we have to calculate IA dash B dash. Now IA dash B dash, which is nothing but what? EAB minus ZA dash B dash, which is equals to what? 50 at an angle 0 by, this is what? 4.64 at an angle 38.7. From this IA dash B dash, which is equals to 7.8 minus 38.7 amperes. That's it. Like that, IA dash C dash, which is equals to VAC by 5, which is equals to minus 50 120 by 5, which is equals to minus 10 at an angle 120 degrees, right? Next we have to calculate find the power reading in the wattmeter. We have to calculate IAA dash. Therefore IAA dash, which is equals to what? Vector addition of IA dash plus B dash, IA dash C dash, right? To get this, we have what? 7.8 at an angle minus 38.7 minus, this is what? 10 at an angle 120 degrees. So from this we can get the value of IA dash is 17.5 at an angle minus 50.69 degrees. This is IAA dash. We have series current, that is current coil current. Then what about voltage between VAB? This is the current through current coil. That's it. Therefore the voltage across the wattmeter is what? VAB only, which is nothing but what? 50 at an angle 0 degrees, right? That's it. Therefore, so we have the voltage across the line, we have the current. This is nothing but what? PC coil voltage, pressure coil voltage. Therefore wattmeter reading, which is equals to what? VAB into IAA dash, right? Which is equals to what? 17.5 into 50 at an angle, what is the current? Minus 50.69 degrees, right? This is what? 554.4 watts, right? This is the wattmeter reading. Note, in case the PC of wattmeter is connected between B dash and C dash, therefore wattmeter reading is what? 17.5 into 50. Sorry, here we have VI cos of this angle, right? Cos phi. We have to write this is what? Cos of this angle. That's it. This is cos, right? Now it is 17.5 into 50 into cos of minus 120, because that is the second phase B and between B and C, plus 50.69. That's it. Okay, which is equals to 309. So like that for C and A, minus 240 plus 50.69. That's it. Okay, yeah. This is about the problems based on three-phase circuits.